Hello everyone. We're going to take a look at our last section for chapter 2, and this section is on continuity. Make sure your cell phones are put away and turned off so you can focus really intensely for the next 10 minutes or so. The section on continuity also includes a little bit of a discussion on one-sided limits, and I know we've talked about one-sided limits already, but I want to be a little bit more formal about it in this section. So remember that in general, for a limit to exist, the function must approach the same value from both the left side and the right side. So in this picture, for example, as we approach 3 coming from the left and from the right, we're approaching the same y value of 2. But a one-sided limit could only look at the function, the limit, from either the left or the right side. So for example, this notation here, the limit of f of x as x approaches 1 from the left only is 0 for this particular graph. But from the right, the limit as x approaches 1 from the right would be coming from this direction. That limit would be 1. Now, if I said to you for this function, what is the limit of this function as x approaches 1? You would tell me d and e, because the left and the right side do not match. So that part still has to be true. The only thing that's different is we could potentially look at it from just one side or the other. And then just a little reminder that f of 1 is the value for the function where basically where the dot is, where the graph is filled in and defined, and that would be right here at 1. So f of 1 is equal to 1. That's this value right here. If I said to you, what is the limit of f of x as x approaches 2 coming from the left? So that would be approaching 2 this way. Looks to me like it would be 1. And as we approach 2 coming from the right, that would be from this side, the limit there would also be 1. And I didn't put it on here, but if I said to you, what is the limit of the function as x just approaches 2, the overall limit, you would tell me 1, because these two things match. Down here I'm asking, this spacing is a little off here, but that's okay. I'm saying, what is f of 2? Notice there's a hole in the graph right here, but it's redefined up here. So f of 2 is 2. That's the value right here. Let's try the next one. The limit of f of x as x approaches 3 coming from the left. Let me get rid of some of my markings here. So as we approach 3 coming from the left, that would be from this side, and that value would be 2. As we approach 3 coming from the right, that would be this side, that value would also be 2. If I said to you, what is the limit of this function as x approaches 3, the overall limit, you would tell me 2, because these two things are both 2. And down here I've got f of 3, and that would be the value right here, which would actually be 2. So all of these things were the same for the value at x equals 3. The next example, we're looking at this graph of the square root of 4 minus x squared. As I approach negative 2 coming from the right, so negative 2 is here, so approaching it from the right means I'm following the graph this way, and that intersects the x-axis right there. That would in fact be 0. You can still use direct substitution even when it's a one-sided limit. So in this example I could have said, what is the limit as x approaches negative 2 from the right, and we would have substituted in the negative 2, and that would have worked as well. We still would have gotten a value of 0. So no problem, even if it's a one-sided limit, we can still use direct substitution as long as the function's defined there. Look at the next example. This is a step function. You can see the graph of this to the right. So the first part says, what is the limit as we approach 0 from the left? So 0, of course, where x equals 0 would be the y-axis. So as we approach 0 coming from the left, we're looking at this part of the function right here, and you can see that that would be negative 1. How about as we approach 0 from the right? That would be this part of the function here, and you can see that that value would be 0. So if I said to you, what is the overall limit for this function as x approaches 0, you would tell me d and e, because the left and the right limits do not match up. Most of the time when we look at functions in calculus, we're interested in where the function is continuous. So this idea of continuity is really important, and we're going to explore that with this definition below. And in layman's terms, we can just think of a function as being continuous because you can draw it without picking up your pencil. There's no holes, there's no gaps, there's no jumps, there's no asymptotes, anything like that. So this three-part definition of continuity at a point is going to be very important. So make sure you take good notes on this section. F is continuous at point C if the limit of the function as x approaches C, if that limit exists. Second, if f of C exists, so in other words, if the function is defined at C. And then finally, if parts 1 and 2 are the same, then we have continuity. So in other words, if the limit of the function as x approaches C, the overall limit, exists, and if that equals f of C, then we know we are continuous at a particular point. Functions that are continuous can be added, subtracted, multiplied, and divided, and we're still continuous. So in other words, we can combine functions in any of these ways, and as long as we're combining continuous functions, the combinations are still continuous. Additionally, so are composites. So in other words, f of g of x. If f is continuous by itself and g is continuous by itself, so is f of g of x. There are two types of discontinuities that we may discuss. One is called a removable discontinuity, and basically this would mean you have a hole in your graph. So if we had a graph where we had something going on where we had a hole, we would call that a removable discontinuity because we could fix it or we could remove it by filling in the hole in a redefinition. And we'll talk about that a little bit more in class. Non-removable discontinuities are basically discontinuities that can't be fixed. Those would involve jumps in a graph. So if we had a graph where kind of like our step function actually back here where we've got a jump in the graph. So maybe something where the graph does this and then maybe up here it does this. So a piecewise function. Maybe it's defined up here but not at the bottom as x approaches C. That would be a jump discontinuity. Another type of non-removable discontinuity would be an asymptote or an infinite discontinuity. So basically if a graph has a vertical asymptote, let's say at C, there's no way to fix that or remove that. So we call that a non-removable discontinuity. Holes we can fix, non-removable discontinuities we cannot. All right, so tomorrow make sure you've got this three-part definition in your notes because that's really important. Tomorrow we're going to explore that a little bit further and look at how we actually test continuity using that definition.